In this video, we'll be discussing about the rational function, what is a rational function and how to find out the maximum and minimum value of the rational function, which we can also say how to find the range of the rational function. Okay. So what is the definition of rational function? Px by qx, where px and qx are real polynomial and qx is not equal to 0, is known as rational function. It means the numerator should have a real polynomial and denominator should also have real polynomials. So for example, if I'll write xk plus 1 by x, is this a rational polynomial? Yes, it is a rational polynomial because the numerator has degree 2, denominator has degree 1. And we can write the domain of this term as x belongs to r minus 0. Okay. Similarly, for next case, the numerator is also a real polynomial of degree 2, denominator is also a real polynomial of degree 2, hence it is a rational function. This is also a rational function, but this is not a rational function because x raised to the power 1 by 3 plus x plus 5 is not a real polynomial. Now, the next case is we have to find the range of the rational function. So there are some steps. So let's look at the method. First, what you need to do is if a rational function is given and you want to find the range, in this particular case we have a constraint that the numerator or the denominator degree should be 2 or less than 2, because we are studying the chapter quadratic equations. So our this method is applicable only in the case where we can get a quadratic equation, or in some cases where the functions can be reduced to quadratic equation. So if the numerator or the denominator degree is 0 or 1 or maximum 2, you can apply this method in case of a rational function. So let's consider the rational function is k and write the domain for that particular rational function. So I'll just take a example side by side so we can easily do the steps and cross check. So the first step is write the rational function as k and write its domain. So the first step is k is equal to x plus 1 by x and the domain is r minus 0. Okay. Now moving on to the second step, make a quadratic in x. Now we have to make a quadratic in x. So the second step is xk minus kx plus 1 is equal to 0. I cross multiplied and made a quadratic in x. Okay. So this is a quadratic in x. Third is a point which you need to remember, that root of the equation in 2 lies in the domain of the rational function. It means that this equation has roots which will lie in this domain of the rational function. You can easily cross check that because this is a quadratic equation and in the domain x is not equal to 0. If I'll try to put x equal to 0 in this particular equation, I will get 1 is equal to 0, which is not possible. It means that if x is not equal to 0 in the domain, x is equal to 0 cannot satisfy this equation. Because x belongs to r minus 0, it means that x square minus kx plus 1 equal to 0, which is the equation we got, must have roots which are real, equal or real distinct. But they cannot be equal to 0. Roots cannot be equal to 0 because it won't satisfy. Okay. Because now the roots are real, equal or real distinct, we have to apply the condition d is greater than or equal to 0, and this will give us the range of the rational function. If the domain is real or real minus alpha beta or real minus alpha, then apply d is greater than or equal to 0, which is discriminant greater than or equal to 0. So if I'll apply discriminant is greater than or equal to 0, I will get k sk minus 4 is greater than or equal to 0, b sk minus 4 ac. So this will give me k minus 2 into k plus 2 is greater than or equal to 0. For solving this, we will get k is less than or equal to minus 2 union k is greater than or equal to 2. Okay, so the values of k will be minus infinity to minus 2 close interval union close 2 to infinity. Okay, so till now we have covered till point 4. Now if suppose the roots are like the domain is like x is greater than 0 or x is less than 0, then there will be other conditions which we'll be covering in the problems we'll be solving. Now last point you need to check always is that is the 6th point. The 5th point is about the different conditions which the roots, the domain of the rational function will apply on the equations, the quadratic equation. Okay, now for the boundary conditions, what are boundary conditions? The boundary conditions are, like suppose if I say we have the condition that d is greater than equal to 0. The equal to 0 case is known as the boundary condition. In some cases it might be possible that you are applying the condition and d cannot be equal to 0. So you have to check the case for d equal to 0. So in the range, whenever you get the equality, you check whether that range is possible or not. That in this case, for d equal to 0 you are getting k as -2, and for d equal to 0 you are getting k is equal to 2. So you just have to check whether we are able to achieve k equal to -2 and k equal to 2 for the domain of the rational function. So the domain of the rational function was r minus 0. Now you can easily see that x plus 1 by x will have value -2 at x is equal to -1, which is in the domain, which belongs to domain of the function. Hence k equal to -2 is possible. X plus 1 by x is equal to 2 is possible at x is equal to 1, which also belongs to domain of the function. Hence k is equal to 2 is also possible. So the final range will be -infinity to -2, close interval, union 2 to infinity, which you have to remember precisely also. So for the function y is equal to x plus 1 by x, when x is negative, the range is -infinity to -2, close interval, and when x is positive, the range is close to infinity. Okay, I hope it is clear. Some more typical problems where the boundary conditions are effective will be discussed in the problems.